तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next. Before we do that, as usual, let us recapitulate what we discussed in our previous lecture. You might recall in our previous lectures we discussed about how operational amplifiers can be used for generating sinusoidal waves, namely the applications of op amps in oscillations. We discussed different types of oscillators, mainly RC oscillators. We discussed, for example, two different types, phase shift oscillator and Wien's bridge oscillator and twin T oscillator are the three different types of RC oscillators that we discussed during the last lecture. Now I want to go on to another very important application of operational amplifier, especially a nonlinear amplifier. This is what is known as the logarithmic amplifier. One of the most useful circuit techniques using op amps is this logarithmic amplifier. When we want dynamic range compression, when that range is going through several decades, then it becomes very difficult to draw the relationship within a simple graph. You would have seen, even when you want to plot, for example, the bandwidth of an amplifier, the frequency will go from about 10 hertz or so to 1 megahertz. So nearly 6 orders of magnitude you have to vary the frequency from 1 hertz to 10 power 6, and so it becomes difficult to plot it in a normal linear graph. So we want to go into a logarithmic scale. In the same way, when for example a sensor or whatever is having a very large dynamic range over several orders of magnitude, then it will be very convenient if I can use a logarithmic amplifier, or in another case a anti-logarthmic amplifier. You would find the whole manipulation of the signal becomes much more convenient for us. So dynamic range compression, raising to powers, taking roots, square roots, RMS conversion, which again involves a squaring, and multiplier divided circuits where you get two analog voltages can be multiplied or two analog voltages can be divided, as the case may be. All these circuits can be designed out of a very basic configuration which is known as the logarithmic amplifier. So we will discuss about the logarithmic amplifier. So what will the logarithmic amplifier do? The logarithmic amplifier will convert a linear voltage given at the input, a current or voltage, whatever that you have, it can be a current or a voltage. At the output you will get the logarithm of this value. So the relationship between the input output is decided by the logarithm. So if I give V in, the output V output will be log of V in, that is what I mean by this. Equally important configuration is the reverse operation, where you get the anti-logarthmic relationship between the input and the output, anti-logarthmic amplifier. So in an anti-log amplifier, if one applies a voltage or a current at the input which is varying logarithmically, the output becomes linear. That is exactly what it does. So, using such log anti-log combinations we can very easily generate multipliers, analog multipliers and analog divider circuits. We all know from basic principles of logarithmic amplifiers, logarithms. No? So, if we want to multiply two analog voltages, input voltages, one way to do that is by taking the logarithm of the two voltages and adding them and then again converting them back to linear by using an anti-log amplifier circuit. From the elementary logarithm ideas, you know, log AB is nothing but log A plus log B, as you can see on the screen. Log A plus log B is equal to log AB. So, if I want the product of two voltages, then I should add the logarithm of each of those, logarithm of A and logarithm of B. Then if I now take the anti-log, then I will get AB, the product. Similarly, if I want a division, you know, log A minus log B is equal to log A by B, and therefore if I use two logarithm amplifier for A and B inputs and get the difference of these two and take the anti-log, use an anti-log amplifier and obtain the output, you will get A by B or B by A, as the case may be, whatever you want. So, obtaining analog multiplication or obtaining analog division is possible by using such logarithmic amplifier. These are some of the applications of the anti-logarithm amplifier. The basic device which is responsible for helping us using an op amp to obtain a logarithm or anti-logarithm amplifier is a diode, semiconductor diode. It is a known fact, you all know, we have seen that again and again, that the base emitter voltage, for example VBE of a silicon transistor, is logarithmically related to the collector current over extremely wide range of values. So, if I now use such transistor diode, silicon diode or silicon transistor in the diode mode, I will be able to generate logarithmic relationship. So, we can use such transistor or a diode, semiconductor diode, and we can build a log converter over easily 5 decades, that is about 100 dB, 10 to the power 5 or 100 dB or more. Okay, now I want to show you an actual amplifier. You can see on the screen, what you see is a looks very similar to a normal configuration of an operational amplifier. You have an input R resistor, and in the feedback you find you have got a diode now. Instead of a resistor you have a diode, silicon diode for example. So, this becomes a simple logarithmic amplifier, just an amplifier, one resistor and one diode, that is all you need. You are able to construct a very simple logarithmic amplifier. What is the principle? I will explain to you. Since this point is a virtual earth, we all know that, because the other non-inverting input is grounded. So, this input is a virtual earth, and therefore, you know, Vs by R is a current here, and this is a current which is actually passing through the diode. So, because the input current into the operational amplifier is very small, negligible, the same Vs by R, which is actually Is, is the one which is also flowing through the diode. So, that is what we are going to do. Is is nothing but If, the feedback which is going through the diode, or Vs minus 0, because the virtual earth point, divided by R is equal to If, which is a diode current, and diode current, you know, is I0 exponential EVF divided by eta kt minus 1. This is the standard diode equation which we have also seen earlier when we discussed about diode. So, if you consider the exponent term compared to the 1, this exponent term is much larger, and therefore I can neglect the 1 term there, and I can approximate this to I0 exponential EVF by eta kt, where eta is a constant associated with the ideality factor, as we call, is associated with the semiconductor that we use. V0 of course is the output voltage, and that will be equal to minus Vf output, because you are measuring the voltage, the current is flowing towards V out, therefore, it has to be a negative voltage. So, V output is minus Vf, and that is minus eta times kT by E ln Vs by I naught R from this equation that we have already got. So, V naught is equal to minus eta into kT by E into ln Vs by I naught R, that is obtained by taking logarithm after you get the thing, so that you can get rid of the exponential. So, where I naught is called the reverse saturation current flowing through the diode. Eta is 1 for germanium and 2 for silicon. T, capital T, is the temperature in Kelvin scale. The small k is Boltzmann constant, it is actually 1.38 into 10 to the power minus 23 joule per Kelvin, and E is the electronic charge, which is 1.6 into 10 to the power minus 19 coulomb. So, all these values are known. So, V naught is equal to minus eta kT by E ln Vs by I naught R, which when I substitute all these values, and I assume 27 degree centigrade, which is the normal room temperature approximately, and so that it becomes, after when I add 273, it becomes 300 degree Kelvin, which is a very convenient number, and therefore I take 27 degree centigrade as my standard. So, when I do that and calculate, we know kT by Q from diode also we have seen is nothing but about 26 millivolt. kT by E or Q, Q is actually the charge, is equal to 26 millivolts approximately, and therefore, if you use this value, V naught becomes about 59 or 60 millivolt logarithm of IC by I naught. IC is the collector current, or in this case the diode current, I naught is that reverse saturation current of the diode. So, at 27 degree centigrade, the VBE of a silicon transistor will increase by about 60 millivolt for each decade increase in the diode current. So, that is what this equation says. Whenever this is logarithm to base 10, so whenever it increases by 1 order of magnitude, I will get an increase of 60 millivolt in the output. So, that is how we look at it. This is the basic equation that we have. So, now that is what exactly I have done. I have substituted the values for the equation. The eta is 2, k is 1.38 10 to the power minus 23, capital T is 300 Kelvin, divided by E is 1.607 in 10 to the power minus 19, and I have assumed a input voltage of 100 millivolt. So, Vs is 100 millivolt I assume. So, and I have assumed also I naught to be about 14 nanoamperes, which is a typical value, 14 into 10 to the power minus 9 into the resistance we have assumed to be 1 kilo ohm. So, when I substitute this, all these values, and I have simplifying this over this, and then you would find it is around 51.5 multiplied by 8.87, this is about 8 orders of magnitude difference, and therefore, the actual value for 100 millivolts is about 0.457, that is 457 millivolts, with negative sign is there. So, it is minus 0.457 volts. So, if I now I am showing you a graph where we can see this variation. I have applied different voltages at the inputs 0.1, 0.2, 0.3 etc., and I looked at the output voltage. You can see when I apply 0.1 it is about 0.6 something, 0.7 we got just now, and as I keep increasing the voltage, because it is negative, it keeps decreasing here in an exponential way. So, this is corresponding to the logarithm, and to see whether it is really logarithm, what I do is I take the logarithm of the output voltage and draw a graph between V in, the logarithm of V in versus V output, the logarithm of V in versus V output. That is what I have done in the next graph. You can see the x axis is logarithm of V in, and output is directly plotted in voltage. So, you find you get a linear graph, that means this is corresponding to the logarithmic behavior, and the slope of the graph is around 0.495, 0.495 is the slope of this graph. So, very simple logarithmic amplifier can be constructed using a diode in the feedback, but we have to also remember what are the drawbacks of these logarithmic amplifiers. Now, you must remember that the temperature factor comes over here in the equation. If you see the screen, V output is equal to eta times kT by E, where T is the temperature. So, when the temperature is changing, the output voltage will be dependent on temperature, so that also will change. And you also have another factor, which is I naught, which is a reverse saturation current of the diode, which is also highly sensitive to temperature. Therefore, there are two parameters in the equation which are temperature dependent, and so one has to be careful when you use an amplifier. It will also have a very severe dependence on temperature. So, people started thinking how to overcome this difficulty, how to compensate for any variation in the temperature. So, what we normally do is we try to use two diodes in the configuration. So, then the graph, now the circuit that I have shown in the screen, you can see it involves two diodes, D1 and D2, right, and I use a current source here, so that the what you will measure, the I naught value will be the difference between these two currents, and therefore the temperature dependence will become very less. I have written it in the equation. For example, V, in this case the V output is equal to eta times kT by E divided by, within bracket, ln of I, which is the current through the current source, ln of I naught, which is the current through one of the diode, ln Vs by R, as we have in the previous case, which is corresponding to the current through the D1, and ln I naught, which is again the reverse saturation current to the other diode. So, you find the two diode, the currents log I naught minus ln I naught will cancel each other, therefore, thereby we will overcome the temperature dependence of I naught, which is coming in the output. So, you would find output becomes independent of that I naught dependence, and therefore, the V is equal to minus eta Vt ln Vs by Ri, where Vt is this quantity kT by E, which is again temperature dependent, but this is the only temperature dependent that is coming here. We have eliminated whatever the effect of the I naught coming into the final expression by using two matched diodes. The usual way of implementing this logarithmic amplifier is not by using diode as I have shown here, but actually using good transistors, because it is much easier to get matched transistors. They will use transistors in the diode mode in the feedback to obtain the actual logarithmic amplifier. So, the expression for the previous circuit that I showed is written here, and you would find the only for except for the Vt factor which is coming, all the other things are completely eliminated. But in the circuit you also see one extra resistor, which is RT. This RT is usually chosen in such a way that RT takes care of the temperature dependence of Vt. You can choose RT suitably, so that will compensate for the change in Vt, thereby we can eliminate both the sources of temperature variation, namely the Vt factor as well as the I naught factor. The normal way I mentioned to you already of making use of a logarithmic amplifier is to make use of a transistor, because in a transistor the current to voltage relationship between the base and the emitter is exactly in a logarithmic scale over a much wider range compared to a normal diode. Therefore, usually we prefer to use a transistor in place of a diode in the feedback scheme. Now, I am showing you another circuit in which I have shown the diode being replaced by a transistor. The base of the transistor is grounded and the collector comes to the virtual earth terminal, and the emitter is going to the output point. So, you can see you measure voltage output between the V output point and ground. Now, you can see the V output point and the ground is nothing but VBE. So, basically you are measuring the VBE as the output voltage. So, and that is actually the collector current is almost equal to emitter current, and the collector current is given by Vi by R as in the screen, and therefore you find the relationship is very similar to what we already discussed. Only difference is instead of a normal diode we are using a transistor. So, I have shown the equations corresponding to that, and it will finally you can see the output voltage is around 60 millivolt, 0.059. If you convert into millivolts it is 60 millivolts approximately, logarithm of Vi by Ri IE naught, which we already discussed. Therefore, it is proportional to logarithm of Vi input. Output voltage is proportional to logarithm of Vi, and the multiplication factor is around 60 millivolt, which we already saw. That is exactly what I have derived here, I have shown you here. So, the circuit produces a change of about 60 millivolts in the output voltage for each decade of change, nearly 10:1 ratio in the input voltage. Now, there is another scheme by which you can also compensate for the temperature dependence, that is what is shown in the next. I will not go into the details, but what you do here, you have used two matched transistors. The two transistors will have almost identical I naught values. So, you would find by using a configuration, again you will find the difference in VBE is what you are going to measure, and this third op amp is basically in the differential amplifier configuration. So, you are looking for the difference in the VBE voltage as the two transistors, and therefore, whenever you take a difference you would find the temperature differences also will be taken care of. It will be completely removed because temperature is constant to both whatever, and you can see the directions of the diodes are different in this case between base and emitter and base and emitter, and therefore, the I naught will get cancelled here. So, you will get a temperature compensated logarithmic behavior when I use this configuration. So, having seen this, let me now show you a demonstration of the simple logarithmic amplifier, and you must remember the slope that we got for the relationship, especially when it is shown in the linear graph, is around 0.049 or 0.05, that is what we got the slope. So, you should remember that we will get for different input voltages approximately with this relationship. That is what I am going to show you now. You can see the circuit here. You can see there is a 1 kilo ohm resistor at the input R, and you have a diode here, and you have the op amp here. The inverting terminal is the one which is in which we are giving the input, therefore, output should be negative of the input, and because there is a diode it will be the logarithm of the input voltage. So, this is the graph, and you can see also below the circuit the diode. I have not used a transistor, I have used only the diode here, normal silicon 1 and 4001 or so, some standard diode I have connected in the feedback. You can see that it is going from 2 to 6, and you have the 1 kilo ohm resistor here which is connected to a millivolt source, which we are also already very familiar, we have used this many times. So, you have a selection range and a continuous variation here, and you have a potentiometer which can vary within the range. So, these three knobs are used to adjust the different values of the millivolts, and that input is given as the input for the logarithmic amplifier. The output of the logarithmic amplifier is monitored using a multimeter, which also I am sure you are all familiar. It is in the voltage range, and you get a minus 0.48, and if you really look at the input voltage, I will take the multimeter and connect it at the input just to see what is the input at this stage, and you can see the input is 0.9, that it is about nearly 100 millivolt. So, let me slightly increase it to make it 0.1. Yeah. So, it is about 0.1. 0.1 means 100 millivolt, 0.1 it is in the voltage range. So, this is 100 millivolt, and when I have 100 millivolt I will again change the multimeter to the output point. I have connected at the output point, and you can see the output is about 0.48. So, when I have 100 millivolt it is around 48. If you remember the linear graph that I showed you, it was very close to 0.49 or something like that. Now, if I make it 0.2 volts at the input, it is around 0.51. So, it is not increasing in a linear fashion, but the increase is only about 0.03, 0.48 to 0.51. So the difference is only 0.03. Now if I go to 300 millivolt, now it becomes only 0.52 or 0.53. So it keeps on decreasing, it is not in a linear fashion. That is what I want you to recognize. Now it is 400 millivolt, for that it is 0.54, and if I go to 500 it is 0.55. So you can see the output voltage is increasing very slowly, whereas the input is going in steps of 100 millivolt. And if you take the set of readings and if you take the logarithm of 100 millivolts, logarithm of 200 millivolts, etc., with reference to base 10 and plot the output voltage, you will get a linear graph, a straight line. So therefore when the input is changing in large amount, the output is changing only very slightly. That is exactly what is known by compression. So several orders, if you vary the input, the output varies only in a linear fashion. Okay. So this is, the input is varied in logarithmic fashion, the output is varying in a linear fashion. That is exactly what we wanted to achieve by using the logarithmic amplifier. So I just want to recall once more. You can see when I have 100 millivolt approximately, you get a 0.48, this is for 200 millivolts, etc., and you can see this follows a simple linear graph. And in the logarithmic scale, in a linear scale, output voltage and input voltage are in linear scale. For 100 millivolt you get 0.6, for about 0.2 it is about 0.51, and 0.3 it is around 0.53 or something. So you can see exactly the way we got in the multimeter, right. Having seen the logarithmic amplifier, now we will move on to the next, which is the inverse operation, which is anti-logarithmic amplifier. So how do you get a anti-logarithmic amplifier? If you recall your integrator and differentiator circuits made using op amp, for an integrator you will use the capacitor in the feedback loop and the resistor in the input side, and if you want to differentiate, you will just invert the two. You will put the capacitor in the input side and the resistor in the feedback loop, then you get a differentiating circuit. In the same way, if I put the diode or the transistor in the diode mode in the feedback loop for getting an logarithmic amplifier, for an anti-logarithmic amplifier, anybody would guess, now I know, that we should put the diode in the input circuit and the resistor in the feedback loop. So it is as simple as that. You can see the circuit that I have shown here. I have used the resistor in the feedback and I have used the diode in the input side. Other than that, there is no other change, just I have swapped the two components. The resistor now is in the feedback and the diode which was in the feedback previously is now in the input side. So this provides you with the anti-logarithmic amplifier. The relation, the equation is very simple, similar to that. So you get minus V naught by R, because you know this is a virtual earth point. So this is minus V naught by R will be the current which is flowing into the output terminal, and that is equal to the diode current I naught exponential EVF by eta kt minus 1. This we have seen, and we neglect the 1 minus 1 here, and therefore we are we get V naught is equal to minus I naught into R. Exponent is nothing but logarithm, invert of logarithm, and EVS by kt. Vs is as input signal that we applied by eta kt, and so when you substitute the various constants for silicon diode 2, etc., and kt by E, the Boltzmann constant and all those things, you find you get about 300 millivolt when I apply around 0.2 volts, right. When I apply about 200 millivolt, I get about 300 millivolt at the output when you simplify the numbers. So I have also shown a graph here, which is a graph between input voltage versus output voltage. You find previously it was like this, right. Now you see the input voltage is in the y axis, the output voltage is in the x axis. So you can see it is following an exponential behavior, and I have not shown you the linear graph in this case, and this also can be implemented as I mentioned previously. Instead of using a diode, you can make use of a transistor. So you are using a transistor here, and the input voltage is actually the VBE voltage of the diode between the emitter and the base. Base is grounded here, so what you apply will be the VBE voltage. Because of this there will be a current generated IE, and that IE is the one which is also flowing through R, and so the relationship as I explained to you previously can be obtained, and when you actually simplify and use, you find IC, the IE or IC both are equal almost, and therefore IC is equal to IE naught e power 38.9 VBE is the relationship that I get. VB is nothing but Vi, and therefore it becomes e exponential 3 at 38.9 Vi. The quantity is now expressed in this form, right. So this is the relationship between the input and the output, and I will now perhaps show you a demonstration of the anti-logarithmic amplifier. So you can see the circuit which is shown here. The diode is in the input circuit of the operational amplifier, and in the feedback I have the 1K resistor. Previously for the logarithmic amplifier they were interchanged, the diode was here and the resistance was here. Now for anti-logarithmic the diode has come here and the resistor here, and there is nothing else except for the op amp. So when I give input voltage, I give input voltage for DC voltages from the millivolt source which we have used even earlier, and the output can be varied in 100, 200 etc. millivolts. I have now kept it in millivolts, 1, 2, 3, 4, that means this is in 100 millivolt, this is 1, 2, 3, 4 means 100 millivolt, 200 millivolt etc. This is the minimum position. So the input voltage is actually connected at the diode. You can see the circuit here, the diode is at the input circuit, and this is the op amp, and in the feedback I have got the 1K resistor. From the color code you can see brown, black, red, this is 1K resistor. So this is a very simple circuit, and now the output is connected to the pin number 6 to a multimeter. As you can see, the multimeter now reads 1.55 or something volts when I give 100 millivolts. So you get a very large output. Previously if you remember, when I changed from 100 to 200, 300 millivolt, it was changing from 0.48 to 0.51, 0.53, it was changing very slowly the output compared to the input. Now what is happening, for a change in input there will be a very large change in the output, exponential increase in the output, because it is a anti-logarithmic amplifier. Now to see what is the input I have given, I take the multimeter and connect it at the input terminal. When I connect the multimeter at the input terminal, you see the multimeter, it shows 1 volt, it shows 1 volt. Now I will make it 100 millivolt. So this is actually, yeah, so this is 0.1 volt, that means 100 millivolts. Now when I have 100 millivolts at the input, I take out again and connect the multimeter at the pin number 6 of the op amp, and you can see it is around nearly 1 volt, 100 millivolt comes nearly around 1 volt. Now when I increase to 200 millivolt, when I increase the input voltage to 200 millivolts, I get about 1.03 or something. So I change to 300 millivolts, now it is 1.12 etc. It has gone to volts now, and when I go to 400 millivolt, it is 1.17 etc. right. So if you actually take the output, it will be related to the input through the logarithmic, that means logarithm of the output voltage will be equal to the input. It is a reverse operation, that is what we should remember. Therefore output voltage will be exponent of some value into the input voltage. That is what we already showed when we discussed the corresponding equation to this. So this is the anti-logarithmic amplifier, where the diode is in the input circuit and the resistor is in the output circuit. We are making use of the relationship of the current through the diode, which I is equal to I naught exponential. So, this is what is being made use of in this configuration for generating the logarithmic relationship. Having seen the logarithmic and anti-logarithmic amplifiers, we also saw the actual demonstration of the circuits using logarithm and anti-logarithm. Now, what are the applications? I mentioned to you already that log anti-log amplifiers can be used for multiplying two analog voltages. There are analog multipliers available in integrated circuit form. You can buy 4 quadrant etc., but then the simple principle behind that is to make use of the logarithmic and anti-logarithmic amplifier. So, what is a multiplier? In an analog multiplier, the output voltage at any time is proportional to the instantaneous product of the two separate input voltages. That is what I mean by multiplier. The operation is achieved by a complex combination of operation amplifier and nonlinear components like the diodes and things like that. Right. Now, what I am going to do is I am going to show you a block diagram of a multiplier. So, you have a Vx and Vy as the two inputs, and you get an output V naught. The cross here shows that it is a multiplier. So, V naught is equal to some constant times Vx into Vy. So, this is the multiplier. This is the characteristic of a multiplier. The output is the product of the two inputs Vx and Vy multiplied by some constant factor k. The quantity Vx and Vy represent the two inputs and V naught represents the output, and therefore, V naught is equal to k into Vx into Vy. Okay. One of the important application of the multiplier is the balanced modulator. When you do modulation, you would find you should have a multiplier, so that you can get the sum and different frequencies corresponding to the two inputs. Okay. How do you achieve division? If I have a multiplier, how to get a multiplier, I already explained to you. You have Vx and Vy initially applied to a logarithmic amplifier, so that the output will be log of Vx and log of Vy. Then you use a summing amplifier, add V log Vx and log Vy. The output therefore is going to be log Vx plus log Vy is nothing but log of Vx Vy. Now, if you put another anti-log amplifier at the output, then you get back your Vx Vy with a constant factor k, and that is the principle of a multiplier in basically. Now, how to achieve division? You can use the same multiplier to achieve division by using op amp. That is what I want to show you. Of course, you can also use logarithmic and anti-logarithmic amplifier and achieve division by subtraction, not by addition. In the previous case, you heard addition, because log a by b is log a minus log b. So, you can use that principle also and obtain division. But here what we are going to do is use a basic multiplying circuit. As you can see in the screen, you use a multiplying circuit, and one input of that you give Vd, which is the denominator voltage, and the actual input of the op amp is Vn, which is the numerator voltage. So, you use two R's here, R and R, they are equal. So, this is the configuration you will use to achieve division using multiplier. If you have, because multipliers are available ready made in the market, you can use multiplier and achieve all other mathematical operations that you want, like multiplication, squaring, division, square root, etc. So, that is what I am trying to show it to you in principle. I am not going to show you any demo of this, but I am only showing you the basic principle behind the multiplier and how the applications of multiplier can lead to different useful circuits. So, now Vd is connected to the one of the input of the multiplier. The V output is the other input of this multiplier, and the multiplier comes in the feedback loop, and the Vn, the numerator voltage, is connected at the input of the op amp, in which this is connected as the feedback device. Right. So, what will be now, if you see what is a Vo prime output of the multiplier now? The output of the multiplier, you know, is k times, where k is a constant, times the two inputs. The two inputs are Vd and V naught. So, VO prime, which is the output of the multiplier, is equal to K times V naught into Vd, which are all the two inputs of the multiplier. And you also know this current, which is Vn by R, is the same which is flowing into this, and therefore V prime VO prime by R should be equal to Vn by R, except that the directions of the current as shown in the figure are opposite. I1 and I2 are opposite in direction. So, that is exactly what is shown here. The I1 plus I2 should be equal to 0. Now, assuming stable ideal linear operation for the multiplier, inverting terminal will be at the ground potential. Therefore, I1 is equal to Vn by R, I2 is V naught prime by R. Therefore, I1 plus I2 is equal to 0, we have already discussed. That means Vn by R plus VO prime by R is equal to 0, or VO prime is equal to minus Vn, that is what we get. So, if I now substitute for V naught VO prime Vn, this will be minus Vn. Minus Vn is equal to K times V naught Vd, and therefore V naught, which is the output voltage that we measure in the op amp, is equal to minus Vn by K times Vd, K times Vd. So, output voltage is nothing but Vn by Vd. Output is proportional to Vn by Vd, and the proportionality constant is minus 1 by K, where K is the factor corresponding to the multiplier that we used. So, Vn is the numerator voltage, Vd is the denominator voltage, and the desired operation of dividing one voltage by another is achieved here, numerator by denominator. So, if you want two voltages to be divided, V1 and V2, you should correspondingly apply the input as shown in the earlier picture that I showed. So, that way you can get division. So, you already got a multiplier. From the multiplier, by using an op amp, you have now achieved a division. Now, how do I get square root operation? How do I apply square operation? That is very simple. The two inputs of the multiplier are connected together. If I give Vi, the output is K times Vi into Vi, K times Vi square. So, squaring from using a multiplier is a very simple elementary operation, there is no difficulty. But how do I get a square root using the multiplier? For that, I have shown you another circuit here. The square root operation can be achieved by again having the multiplier in the feedback loop, but connecting the two inputs together, connecting to the output, and the input is as usual in the previous case you had for the division, the same way you have. So, VO prime is equal to K times V naught square, because V naught is the, both the inputs are now V naught for the multiplier, therefore K times V naught square, and Vi by R is equal to minus VO prime by R, that also we saw previously. Therefore, it will be VO prime will be minus Vi. So, you get minus Vi, or Vi will be minus K times VO square, or VO will be root of minus Vi by K. So, you find the output voltage is square root of Vi, the input voltage. There is a factor K which is coming in the denominator, which is corresponding to the multiplier relation, and there is also a negative sign. So, you can apply negative voltages and obtain positive values for this. So, by using this configuration, you may be able to achieve square root of a given voltage can be obtained at the output. So, this amplifier is a square root amplifier. If I give a Vi, the output is root of Vi, proportional to root of Vi, that is what I get. So far what we have done is I have explained to you how a logarithmic amplifier can be constructed using a diode, and how anti-logarithmic amplifier can be constructed by just replacing the diode and switching the diode and the resistor in the feedback network. And then I also told you how we can achieve multiplier using anti-log amplifiers, and using multiplier how we can achieve squaring, division, and also square root. I would like to give you one more application of the operational amplifier with reference to the diode, absolute diode, that we already discussed in one of the earlier lectures. So, that is to form an AC millivoltmeter using a operational amplifier and a bridge configuration of the diode. That is what I wanted to discuss today. Now, I have shown the circuit here. It is almost clear to you. We have discussed this earlier. So what I have done now is I have used a bridge rectifier. This is a bridge rectifier, many of you are very familiar already. So the output of the bridge rectifier, I connect a milliammeter current meter, and the other ends of the bridge rectifier are connected in the feedback of an operational amplifier, and I have a R at the input which is connected to ground. So it is in the non-inverting mode. It is in the non-inverting mode with the diode bridge in the feedback loop, and the output of the diode connected to milliammeter. The other ends of the diode bridge is connected to the in the feedback area. Now this is a V in input voltage that I give. Now we already saw the advantages of using operation amplifier along with the diode. When I use an operation amplifier along with the diode, you find normally the diode, if it is a silicon diode, the cut-in voltage is around 0.65 or 7 volts, 0.7, which is 700 millivolt. That means if I give a very low signal AC, about 200 millivolts peak voltage, then what is going to happen is, even to make the diode conduct, you require about 600 to 700 millivolts, and therefore there will be nothing which is coming out of the diode, because the diode will not be conducting well at that very low voltage. But if I use an op amp in the feedback and put the diode in the feedback, then you know I can have reduction in the cut-in voltage by 0.7 by the AOL, which is the open loop gain of the operational amplifier. So if it is 0.7 volts for silicon divided by 10 to the power of 5 or 100 kilothousand, which is a typical value of the open loop gain of the operational amplifier, then you can see that you get about 7 microvolts only as a cut-in voltage. So this is the same principle I am using in this case to form an AC millivoltmeter or microvoltmeter. So when I have very small voltages of the order of millivolts, if I put a diode bridge, then the diode bridge, you have two diodes conducting for one side of the AC, one half of the AC signal, and the other two diodes are made use of during the other half cycle, and because the diodes are coming in the feedback loop of an operational amplifier, the cut-in voltage of the diodes will be 7 microvolts each. So 7 plus 7, 14 microvolts will be the voltage that will be lost to make the diode conduct in either direction, and therefore whatever input voltage I give will be available at the output with the corresponding gain factor corresponding to the non-inverting amplifier, because the configuration that I use here is non-inverting amplifier. This R is there, the feedback effective resistance of this will come into the game, and what you will see will be a very nice AC millivoltmeter made out of a basic operation amplifier and a diode bridge in the feedback. So I have shown you a typical reading that we have taken just now using such a circuit. You have the input voltage which is varied from 100, 200 etc. millivolts, and the output current we have measured, and when we draw a graph you get a linear graph. That means the output current meter can be directly calibrated in terms of the input millivolts that you want to measure. So this becomes in that sense a AC millivoltmeter, and we have done that in a very inexpensive way by using the operational amplifier, which is not very expensive these days, and the diodes, which are also very cheap. So by using this, you will be able to have a very nice AC millivoltmeter constructed for our purpose. And if you look at the slope of the graph, the line, the red line that you see on the screen is actually the fitted line using the standard software. So the points are all lying on the same straight line, and therefore the slope is around minus 0.9 millivolt. That is what I get in this typical case. So you can try this type of a circuit easily and then construct a very nice AC millivoltmeter. Now I would like to show you a demo of the AC millivoltmeter. So I want you to see the circuit here. So this is a bridge rectifier that I already mentioned to you using 4 diodes, and that is coming in the feedback loop of the operational amplifier, and you have a 1K resistor and it is grounded at the inverting terminal, and the output of this bridge rectifier at the two ends we connect a millivoltmeter. This is a millivoltmeter. Now this is the op amp and the input is given at the pin number 3 corresponding to the non-inverting input. So you see here the 4 diodes connected in the bridge configuration, the operational amplifier and this 1K resistor which is connected to the ground. So the same circuit is wired here, and the multimeter here is in the current mode and it is in the milliampere mode, and it is in DC because the output is going to be a DC. Therefore this is a DC milliammeter that is connected here. The multimeter is connected as a DC ammeter, and on this side you have the voltmeter which is kept as a voltmeter as such, AC range, and I have a signal generator which is now maintained at 100 hertz approximately 0.1 kilohertz, that is 100 hertz, and you can vary this output voltage, and these are all for offset and things like that. We are going to use only this is for changing the amplitude and this is for changing the frequency. Now I am going to change this, and I want you to see here at the input and correspondingly see at the output at the current meter. So let me now first increase to bring it to about 100 millivolts approximately. Yeah, so this is about 100 millivolts. So I have kept around 100 millivolts, 0.1 volt, 100 millivolt AC from the function generator at 100 hertz frequency. Now let us see what is the output. The output is about 0.74 milliamperes, 0.74. Now I increase the input to some 200 millivolts, let us say. Yeah, this is about 200 millivolt and it is not changing. So I have here 200 millivolts. So I have here 200 millivolts as the input AC, and the corresponding output is about 0.18. That relationship is around 0.9. So 200 into 0.9 is about 180, that is what is shown here. So 0.18. Now I increase it to some 300. So it is about 300. 300 into 9 is around 27. So you get about 0.2728 here. So if I go to 400 millivolts or 500 millivolts, so this is around 500 millivolts, it should be around 45 or 0.48 or something what you are getting. So there is a relationship about 0.9 between the input and output, which is decided by the effective resistance of this 1 plus R2 by R1, that is a non-inverting amplifier gain. So you can see even for 0.5 volts you are able to get output current which can be calibrated in terms of the input millivolts. So as I increase to 600 millivolt or 700 millivolt, let us say. So this is about 700 millivolt, and that is around 60 milliampere current, 0.60, that means 60 microampere current is 600 microampere current is what I get here. So you can see for very low voltages also you are able to get significant current which can be calibrated in terms of the millivoltmeter. Therefore this becomes a AC millivoltmeter, making use of an op amp and a simple diode bridge. Using an op amp and a diode bridge we are able to make a AC millivoltmeter, which otherwise will be a very expensive equipment when you want to buy commercially. But if you slightly improve the performance by adjusting the offset and things like that, you can get a very reliable performance of your AC millivoltmeter, and it will be very inexpensive, and you can buy it, make it in a very easy method. So what we have seen in this lecture is 3 different aspects. One is a basic logarithmic amplifier, and the other one is anti-logarthmic amplifier, and I also showed how this logarithmic amplifier and anti-logarthmic amplifier can be used for obtaining analog multiplication, squaring of the input voltage or square root of the input voltage or division of the input voltage, and I also showed you the actual demonstration of an analog anti-log and logarithmic amplifier. Finally, before closing, I also showed one other application of the operation amplifier, basically with reference to a measurement of very low AC signals of the order of millivolts by using very simple configuration of a bridge diode as well as an operational amplifier. Using a bridge diode configuration in the feedback of an operational amplifier, I showed you that we can construct a very simple AC millivoltmeter. When the input voltage is in very low voltages, millivolts and microvolts, the output can be a significant current, and it can be calibrated in terms of the AC millivolt, and you can get a very inexpensive AC millivoltmeter made out of an operation amplifier and a diode bridge. So in the next lecture I would like to discuss about some of the filters that can be configured using operation amplifier. They are called the active filters. I have already discussed the applications of filters when I discussed about the RC network earlier. You have simple RC network can be used as a filter, but they are called passive filters. You can also have active filters made out with the help of operation amplifier. So we will discuss the different configurations of the filter circuits using operation amplifier in my next lecture. Thank you.